Joycerel May B.Taring from BSED-SCIENCE 1, and today I'm going to discuss Unit 7, Understanding the Past from Stratigraphic Records. Nature of Stratigraphic Records, Fundamental Laws of Stratigraphy, Law of Superposition, and Faunal Succession. Nature of stratigraphic record. So what is stratigraphy? Stratigraphy is a branch of geology concerned with the study of rock layers or strata and layering or stratification. It is primarily used in the study of sedimentary and layered volcanic rocks. Stratigraphy has three related subfields: lithostratigraphy or lithologic stratigraphy, biostratigraphy or biologic stratigraphy, chronostratigraphy or stratigraphy by age. Stratigraphy is a scientific discipline concerned with description of rock succession and their interpretation in terms of a general time scale. It provides a basis for historical geology, and its principles and methods have found application in such fields as petroleum geology and archaeology. Stratigraphic studies deals primarily with sedimentary rocks but may also encompass layered igneous rocks, example, those resulting from successive lava flows, or metamorphic rocks formed either from such extrusive igneous material or from sedimentary rocks. Nicholas Steno. Catholic priest Nicholas Steno established the theoretical basis for stratigraphy when he introduced the law of superposition, the principle of original horizontality, and the principle of lateral continuity in a 1669 work on the fossilization of organic remains in layers of sediment. Nicholas Steno's work on the formation of rock layers and the fossils they contain was crucial to the development of modern geology. The principles he stated continue to be used today by geologists and paleontologists. William Smith. The first practical large-scale application of stratigraphy was by William Smith in the 1970s and early 19th century. Known as the father of English geology, Smith recognized the significance of strata or rock layering and the importance of fossil markers for correlating strata. He created the first geologic map of England. So, now let's start to discuss the subfields of stratigraphy. So, one of these is lithostratigraphy. Lithostratigraphy is the classification of body of rocks based on the observable lithological properties of the strata and their relative stratigraphic position. Variation in rock units most obviously displayed as visible layering due to physical contrast in rock type. This variation can occur vertically as layering or bedding, or laterally and reflects changes in environments of disposition known as facies charge. These variations provide a lithostratigraphy or lithologic stratigraphy of the rock unit. Key concept in stratigraphy involves understanding how certain geometric relationship between rock layers rise and what these geometries imply about their original depositional environment. The basic concept in stratigraphy, called the law of superposition, states in an undeformed stratigraphic sequence, the oldest strata occur at the base of the sequence. So, under lithostratigraphy is chemostratigraphy. Chemostratigraphy includes the studies in the relative proportion of the trace elements and isotopes within and between lithologic units. Carbon and oxygen isotope ratios vary with time, and researchers can use those to map subtle changes that occur in the paleo environment. This has led to the specialized field of isotopic stratigraphy. So under lithography, there's also cyclostratigraphy. Stratigraphy documents the often cyclic changes in the relative proportion of minerals, particularly carbonates, grain size, thickness of sediment layers or barbs, and fossils diversity with time, related to seasonal or longer-term changes in paleoclimates. So, now let's proceed to the second subfield related to stratigraphy. The biostratigraphy or paleontologic stratigraphy is based on fossils evidence of the rock layers, strata from widespread location containing the same fossil fauna, flora are said to be correctable in time. Biologic stratigraphy was based on William Smith's principle of faunal succession, which predated and was one of the first and most powerful lines of evidence for biological evolution. It provides strong evidence for the formation or speciation and extinction of species. The geologic time scale was developed during the 19th century based on the evidence of biologic stratigraphy and faunal succession. These time scales remain a relative scale until the development of the geometric dating, which was based on an absolute time framework, leading to development of chronostratigraphy. One important development is the Veil curve, which attempts to define a global historical sea level curve according to interferences from worldwide stratigraphic pattern. Stratigraphy is also commonly used to delineate the nature and extent of hydrocarbon-bearing reservoir, rock, seals, and troughs of petroleum geology. And the last subfields related to stratigraphy is chronostratigraphy. Chronostratigraphy is a branch of stratigraphy that places an absolute age rather than a relative age on the rock strata. The branch is concerned with deriving geochronological data for rock units, both directly and inferentially, so that a sequence of time-relative events that created the rock's formation can be derived. The ultimate aim of chronostratigraphy is to place dates on a sequence of deposition of all rock within a geological region, and then to every region and by extension to provide an entire geologic record of the Earth. A gap or missing strata in the geological record of an area is called a stratigraphic hiatus. This may be the result of a halt in its position of sediment. Alternatively, the gap may be due to removal by erosion, in which case it may be called a stratigraphic vacuity. It is called a hiatus because this position was on hold for a period of time. A physical gap may represent both a period of non-deposition and a period of erosion. A geologic fault may cause the appearance of a hiatus. Magnetostratigraphy. Magnetostratigraphy is a chronostratigraphic technique used to date sedimentary and volcanic sequence. The method works by collecting oriented samples at measured intervals throughout a section. Example of magnetostratigraphy: magnetic strips are the result of reversal of the Earth's magnetic poles and seafloor spreading new oceanic crust is magnetized as it forms and then it moves away from the mid-ocean ridge in both directions with time, related to seasonal or longer-term changes in paleoclimates. The samples are analyzed to determine their detrital remanent magnetism or DRM, that is the polarity of Earth's magnetic field at the time a stratum was deposited. For sedimentary rocks, this is possible because as they fall through the water column, very fine-grained magnetic minerals behave like tiny compasses orienting themselves with Earth's magnetic field. Upon boreal, that orientation is preserved for volcanic rocks. Magnetic materials which form in the melt orient themselves with the ambient magnetic field and are fixed in place upon crystallization of the lava. Oriented paleomagnetic core samples are collected in the field's mudstones, siltstones, and very fine-grained sandstones are the preferred lithologies because the magnetic grains are finer and more likely to orient with the ambient field. During deposition, if the ancient magnetic field were oriented similar to today's field or north magnetic pole near the north rotational pole, the strata will retain a normal polarity. If data indicate that the north magnetic pole were near the south rotational pole, the strata would exhibit reverse polarity. Results of individual samples analyzed by removing the natural remanent magnetism NRM to reveal the DRM. Following statistical analysis, the results are used to generate a local magnetostratigraphic column that can be compared against the global magnetic polarity timescale. This technique is used to date sequences that generate rock fossils, interbedded igneous rocks. The continuous nature of the sampling means that it is also a powerful technique for the estimation of sediment accumulation rate. A common goal of stratigraphic studies is a subdivision of sequence of rock strata into mappable units, determining the time relationship that are evolved and correlating units of sequence or the entire sequence with rock strata elsewhere. Following the failed attempts during the last half of the 19th century of the International Geological Congress (IGC), founded year 1878, to standardize a stratigraphic scale, the International Union of Geological Sciences, or IUGS, founded year 1961, established a commission on stratigraphy to work toward that end. Traditional stratigraphic schemes rely on two scales: a time scale using ions, eras, periods, epochs, ages, and chronos, for which each unit is defined by its beginning and ending point, and a correlated scale of rock sequences using systems, series, stages, and chronozones. These schemes are used in conjunction with other dating methods such as radiometric dating, the measurement of radioactive decay, the paleoclimate dating, and paleomagnetic determination that in general were developed within the last half of the 20th century, have led to somewhat less confusion of nomenclature and to even more reliable information in which to base conclusion about Earth history. Because oil and natural gas almost always occur in stratified sedimentary rocks, the process of locating petroleum reservoir traps have been facilitated significantly by the use of a stratigraphic concept and data. An important principle in the application of stratigraphy to archaeology is the law of superposition, the principle that in any undisturbed disposition, the oldest layers are normally located at the lowest level. Accordingly, it is presumed that the remains of each succeeding generation are left on the debris of the last. So let's proceed to the fundamental laws of stratigraphy, law of superposition and faunal succession. Today, the geologists and paleontologists makes observation over the new rocks discovered with the help of a stratigraphic section. Diagrams of the strata interversal section. This kind of observation could not be possible until 1669, 1669, when Nicolastino made some diagrams based on the observation on the sedimentary rocks of Tuscany. His short familiar work, Do Soledo Entra Soldum Naturaliter Contento Dissertationes Produmus, provisional report on solid bodies, natural embedded in other solids, included several propositions that helps scientists to examine and study all kinds of rocks. Even if this documentation was abstract or based more on superposition, they represent the main source of inspiration for the pioneers of this field. More importantly, he outlined the principles that are base of the geological researches. So Steno's laws of stratigraphy, the Steno's principle of superposition. At the time when any given stratum was being informed, all the matter resting upon it was fluid, and therefore at the time when the lower stratum was being informed, none of the upper strata existed. The first and most important principle it is today fairly obvious, but in that period, it was far to be considered like this. Known as the principle of superposition, it is said that the sedimentary strata are deposited in the layers, with older one on the base and new on top. With long time before anyone could determine the absolute age of rocks, geologists could rely on the Steno's principle to determine at least which strata is much older. Today, we restrict this principle to sedimentary rocks which were understood differently in Steno's time. Basically, he deduced that rocks were laid down in vertical order to just as sediments are laid down today, now on top of old. This principle allows us to piece together the succession of fossils' life that defines much of the geologic time scale. Steno's principle of original horizontality. Strata either perpendicular to the horizon or inclined to it when at one time parallel to the horizon. Steno's reasoned that strongly tilted rocks did not start that way, but were affected by later events, either upheaval by volcanic disturbances or collapse from beneath by cave-ins. Today, we know that some strata start out tilted, but nevertheless, this principle enables us to easily detect unnatural degrees of tilt and infer that they have been disturbed since their formation. And we know of many more causes from tectonics to intrusion that can tilt and fold rocks. Steno's principle of cross-cutting relationship. If a body or discontinuity cuts across a stratum, it must have formed after that stratum. This principle is essential in studying all kinds of rocks, not just sedimentary ones. With it, we can untangle intricate sequences of geologic events such as folding, deformation, and emplacement of dikes and vines. The Grand Canyon provides an excellent illustration of Steno's laws. Distinctive rock layers, such as cabled limestones, can be matched across the broad expanse of the canyon. We can know these rock layers were once connected, which is described in the rule of lateral continuity. Finally, the Colorado River cuts through all the layers of sedimentary rocks to form the canyon. Based on the principle of cross-cutting relationship, the river must be younger than all of the rock layers that it cuts through. Materials forming any stratum. Steno's principle of lateral continuity. Materials forming any stratum were continuous over the surface of the earth unless some other solid bodies stood in the way. This principle allows Steno to link identical rocks on opposite sides of this principle allowed Steno to link identical rocks on opposite sides of the river valley and deduce the history of events, mostly erosion, that separated them. Today, we apply this principle across the Grand Canyon, even across ocean, to link continents that once were adjoined. Steno's laws of constancy of interfacial angles. In the plane of the crystal axis, both the number and the length of the sides are changed in various ways without changing the angles. The other principles are often called Steno's laws, but this one stands alone at the foundation of crystallography. It explains just what it is about minerals crystals that makes them distinct and identifiable even when their overall shapes may differ. The angles between their faces, it gives Steno a reliable geometrical means of distinguishing minerals from each other as well as from rock, lost fossils, and other solids embedded in solids. Steno did not call out his law and his principle as such. His own ideas of what was important were quite different, but I think they are still worth considering. He put forth three proportions, the first being this. Steno's original principle 1. If a solid body is enclosed on all sides by another solid body, of the two bodies that once first became hard, which in the mutual contact expresses on its own surface the properties of the other surface. The official principle pertains to layers of rock and their shapes and orientation. Steno's own principles are strictly about solids within solids, which of those things came first, that one that was not restricted by the other. Thus, he could confidently state that fossil shells existed before the rock that enclosed them, and we, for example, can see that the stones in a conglomerate are older than the matrix that encloses them. Steno's original principle 2. If a solid substance is in every other way like another solid substance, not only as regards the condition of surface, but also as regards the inner arrangement of parts and particles, it will also be like it as regards the manner and the place of production. Today, we might say, if it walks like a duck and quacks like a duck, it is a duck. In Steno's days, a long-running argument centered around fossil shark teeth known as glossopetrae, were there growths that arose inside rocks, remains of once living things, or just weird things put there by God to challenge us? Steno's answers were straightforward. Steno's original principle 3. If a solid body has been produced according to the laws of nature, it has been produced from a fluid. Steno was speaking very generally here, and he went on to discuss the growth of animals and plants, as well as minerals, drawing on his deep knowledge of anatomy. But in the case of minerals, he could assert that crystals are created with outside rather than grow from inside. This is a profound observation that has ongoing application for igneous and metamorphic rocks, not just the sedimentary rocks of Tuscany. Today, the geologists and paleontologists make observations over the new rock discovered with the help of stratigraphic section, diagrams of the strata is transversal section. This kind of observation could not be possible until 1669, when Nicholas Steno made some diagrams based on the observation on the sedimentary rocks of Tuscany. Even if this documentation was abstract or based more on supposition, they represent the main source of inspiration for the pioneers of this field. More importantly, he outlined the principles that are based of the geological researches. These are the questions that I created. So that is all my discussion. Have a great day. Thank you. Bye-bye.